All right, everyone, welcome. My name is Scott, and I will be teaching you this crash course on engineering statics, or otherwise known as engineering mechanics. So this course is modeled off of the Virginia Tech ESM 2104 engineering mechanics course. In this course, we will be talking about, of course, an introduction to all the statics topics. We will be talking about force systems, both two-dimensional and three-dimensional force systems. We'll be talking about equilibrium, right? So solving for unknowns, solving for equilibrium forces. And then we will also be talking about structures, them being trusses, machines, and we'll also be talking about the different types of methods in order to figure out the unknowns within those systems. Next, we'll be talking about distributed forces. So if you have a beam and you have some stuff going on in the beam, so we could figure out what is going on in the beam itself. Next, we will be talking about some tools that we will end up using in our future classes, like deforms and dynamics. Such topics include centroids and area moments of inertia. And then lastly, we will talk about some other topics such as friction, and I do like to go into real-world applications as well. So, who is able to take this course and who is able to get use from this course? So, first of all, it's primarily designated towards folks who are going to be taking the course in an upcoming semester. Of course, you can use this while you are taking the course as well. So if you're currently enrolled in a summer class, or if you're looking at this course during the semester, it is most definitely going to be helpful. I condensed all the material into 8 hours of lecture and approximately 30-ish pages of notes, which is quite a bit less than the 45 hours of lecture or something like that that you get for the entire course. And with that, you can also use this course as a reference after you've already taken the course and you're going to review, for example, before taking engineering deforms, which there will also be a course available for deforms as well, and you can just look that up on my page. Great. So today I wanted to go over the introductory topics in statics. Of course, the first question we need to answer is what is statics? Then we're going into the approach to problem solving. I'll teach you the method that I use in order to tackle all types of engineering mechanics problems, whether it be statics, dynamics, deforms, or even like further down in the line, we do vibrations or we do other crazy stuff like that. Next, of course, this would not be a statics course without talking about vectors, right? Scalars, vectors, of course, projections and components, and then we'll be talking about an introduction to Newton's laws and a brief review on units, which should have been covered in the physics course. So on this webpage or the course, there should be a set of notes, and everything that I will be teaching should be inside the notes. Now, I designed it so that you can, of course, follow along. You don't really need to write a whole lot of things down, but I tried to leave space in each page in order for you to do so. All right, so let's get rolling. So, what is statics? So the statics is the study of stuff that simply doesn't move. Okay, so in this particular course, we are only concerned with external forces and internal forces. Okay, so we are not concerned with any sort of materials. We're not concerned with like deflection. You know, that will be for the next course. All right. So in addition to not caring about those things, we also don't care about material properties either, like, you know, for example, like density or hardness or anything like that. Okay. So this is how we're going to approach problems my way. Okay, so the first thing that we ever need to ask ourselves whenever approaching a mechanics problem is, what's going on? Okay, so the question is, I need to look at any system, okay, and ask, what is happening in this system? Okay, even if it's not moving, what is going on? So for example, I can take you over to my bike rack over there. All right, so what I've got here is this system, which is just my bike. Hanging on the wall, it's freestanding, right? So there's nothing underneath supporting it, right? I can kind of swing it up and down like this. So the question is, what is going on in this problem? Of course, there's this hook here, right? That's supporting my bicycle, okay? So the first thing I need to look at is, what is actually preventing my bike from falling off the wall, okay? Because upon first sight, you'd be like, well, this system doesn't really look like it should work, right? But if we look deeper into it, we find out that this system actually makes a lot of sense, okay? So the first thing we need to look at is what is going on. Well, first, the bike has some weight, right? And the weight is directed downward, all right? And what's counteracting that weight is this, right? Which is a bicycle holder that is attached to the wall, and studs. If it weren't, it would just rip out the sheetrock, right? So this thing supports a vertical force going upward, all right? And then what? Well, I know that the wall is pushing my back tire out this way, okay? And therefore, I'm thinking that these screws are preventing this bracket from falling off the wall. Okay, so that is the idea that we need to look at with every single problem. Now, this is a fairly simple problem. We'll probably be doing something like this as an example later on in the course. But for now, we need to understand how systems work, right? And be able to describe them with words before actually tackling them with math and mechanics. All right, so back to the whiteboard. All right, we're back. So after we find out what is going on mechanically in the system, then we can implement some equations. So step 3 is what equations am I allowed to use in this particular problem, okay? So each scenario will ask you to use a different set of equations. Of course, we will go over all of those as we progress through the course. So the last thing, after you do all this math, is to ask yourself, does my answer make sense? Now, this question is very interesting. So you may be asking yourself now, how do I determine if my answer makes sense? I don't know what the right answer should be, okay? Now this, of course, comes with a bit of intuition, but in general, we can ask ourselves the following questions in order to make sure our answer makes sense. First, do you expect your answer to be positive or negative, right? In this course, the positive or negative does mean something, okay? So sometimes it'll ask you for simply the magnitude, or sometimes it'll ask you for a positive or negative value which indicates something. We'll go over that later on in the course, okay? And the next one is, do you expect your answer to be large or small, right? So if I get an answer that's like, oh, this apple should weigh 1,000 pounds, you might think to yourself, well, wait a minute, that's probably wrong, so what should the answer be? Oh, I'm off by 3 zeros, right? It should be about 1 pound. Okay, so if you get something that's really off by an order of magnitude or a couple orders of magnitude, then you know that you have to go back to the drawing board and figure out what you did wrong. And the last one is the direction. Okay, so what direction do you expect your answer to be in, right? So it kind of goes back to the positive or negative thing, which of course indicates direction, but more importantly, do you expect something to be going up, down, left, or right? Okay, so as we go through examples with these problems, we will be using these 4 steps in order to solve problems. All right. Okay, so on to the first real topic of this course. So this is going to be scalars and vectors. It's page 2 of the notes. The first part of it should mostly be a review from physics, but after that we start getting into some other applications of vectors. So the first thing I want to do is define what scalars and vectors are. Okay, so a scalar is magnitude only. Okay, and an example of this would be like, oh, a speedometer in your car only tells you how fast you're going, right? So for example, 70 miles per hour, it does not tell you where you're going, okay? Whereas a vector tells you both magnitude and direction. Okay, and I can write that as v times v hat. So you may be wondering, okay, well, what are all these v's and why do some of them have hats and why do some of them have arrows? Well, this is the general form of a vector. I'll show you some other notations in a minute, but this is generally how we represent a vector, and this is the magnitude, right, which is a scalar, and this is a unit vector, which has magnitude of 1. Okay, so this value right here, which is, I said, is a scalar, can also be written as sort of like the vector with absolute value signs, okay? And that will tell us, right, and there's a computation that we can use in order to figure out what this is, which again, I'll go over in a second. All right, then we can also say, of course, that V is equal to the magnitude of V multiplied by V hat. And if I divide by this on both sides, then I get V hat is equal to the vector V divided by the magnitude. And this is going to be a classic way of finding our unit vector V, all right? And suppose that my unit vector V is written as, my vector V is written as Vx I hat plus Vy j hat plus Vz k hat. Okay, so maybe you're wondering, okay, well, what do those things mean? Well, in general, you have a 3D coordinate system. For those of you who are taking multi in conjunction with this course, a lot of the topics and concepts will overlap, especially, of course, because statics, we do use a little bit of calculus, and in multi, we use a very similar coordinate system. Okay, the I hat direction is the x direction. The j hat direction is the y direction, and the k hat direction is the z direction. That's all it says. It just says that my Vx is this in the x direction, Vy is this in the y direction, of course Vz is the velocity in the z direction. Okay, so this is sort of like a fancy notation. When you get to dynamics, for those of you who are taking dynamics, this notation will become a lot more useful, but for now, in my opinion, it's a little bit more complicated than it needs to be. So I prefer to write it as Vx, Vy, and Vz. All right. So it's much more condensed, it's much easier to look at, right, in this form than it is in this I hat, j hat, k hat form. All right. Now the question is, how do we find the magnitude of this vector using this? Okay, so if I were to do that in 2 dimensions, you may already say, well, it's just the square root of the x component squared plus the y component squared, right? Which would, of course, emulate the Pythagorean theorem. It turns out that the Pythagorean theorem also works in 3 dimensions. So we can actually find the magnitude of V by taking the square root of Vx squared plus Vy squared plus Vz squared. Okay, and that is going to be the case every single time. Just a note, obviously, because everything's squared, we don't care if it's going to be positive or negative. Okay, so if you have a negative value for Vy, don't worry, once you square it, the negative will go away. Okay, in order to prevent having mistakes when you do this, because if you type in negative Vy squared into your calculator, it will actually give you a negative value. You need to make sure that you plug it in like this. So when I'm doing this formula, I tend to just put positive numbers in just to avoid making this error right here. Okay, great. So one of the applications to using vectors is projections. Okay, so what is a projection? So a projection is used to find the value of a vector that goes in a particular direction. Okay, so suppose I have a vector V that goes in this direction. Okay, of course it has a magnitude of V, the bars. Okay, and I'm interested in its component along the AB direction. Okay, I'm interested in the component along the AB direction. I know that it makes an angle theta with this dotted line of AB direction. Okay, so in order to find that, what I'm going to do is draw a parallel line down, or not parallel, a perpendicular line from this dotted line to the tip of my vector as such, right? Like this. And then the projection along the direction AB will be this value right here, okay? And this is written as the projection of V in the direction AB, like this, okay? So we can see that this suddenly becomes a simple trig problem where we can just say, oh, well, isn't this just equal to V times the cosine of theta, right? Because this is the adjacent side to theta. So we're like, okay, nice, right? So we were able to figure out the value, okay, of the projection in this direction. But one of the things that we're actually missing is that this itself is a scalar, okay? This itself is a scalar. So it does not take into consideration the actual orientation of AB. What it does is it only uses the relative orientation of V with respect to AB, right? Because theta tells you how far apart V is from AB. Now, if you knew the direction of AB, then you can actually say, oh, this thing goes along AB. Therefore, I actually know the real direction of this red line right here, okay? So, as I wrote in the notes, it says, what if theta is unknown and AB is known, right? So I know the vector V, I know, like, for example, this point A right here, and this point B right here. How do I figure out the projection, okay? So it turns out that we can actually do the following. We can also write the projection as V dotted with the vector AB, okay? And not just any vector of AB, because I don't actually care about how long this dotted line is. Can I say that I only care about the unit vector of AB? Okay, the unit vector of AB, which has a magnitude of 1. Okay, so therefore I can also rewrite it as, oops. Okay, so the question is, how do I do this? And I'll actually do an example in a little bit. I just want to get through some more of the boring notation stuff before we do any real numbers. Okay, so that is how we find, right, the scalar projection. Okay, and one thing I'll actually note is how to find a vector projection, which we'll actually do towards the bottom of the page, it looks like here. All right, so the general case for this scenario turns out to be the following. If I have a vector u and v, if I have a vector u and v that are separated, and we don't necessarily need to know the angle between them, okay? We can say that u is equal to ux, uy, and v is equal to vx, vy, then the projection of v onto u is going to be equal to the magnitude of v multiplied by the magnitude of u multiplied by cosine of theta between them. Okay, which also happens to be the dot product between these two vectors. Okay, so you might be wondering, okay, what is the dot product? Okay, now this is something that you may or may not have covered in physics, so I will go over this a little bit more in detail. So the dot product here is also known as the inner product, and it's one of the ways that we can multiply vectors together. Okay, it turns out that we can actually write it just as you would expect, ux comma uy times vx vy, like this. And when we multiply it together, what we're actually interested in doing is multiplying these together, okay, and then adding it to these two that are already going to be multiplied together. So the definition of the dot product turns out to be ux times vx plus uy times vy. And notice that ux, vx are both scalars, uy, vy are also both scalars. So when we dot them together, we get a scalar that comes out, right? A single number, okay? So we're like, okay, well, I wrote this whole big thing here, but essentially what you need to take away from this is this, okay? And this says that if you know the value of two vectors, okay, of course you can find their magnitudes using the Pythagorean theorem, right? And if you know those two vectors, that means that you're able to find the angle in between them. So this angle is able to be found with this equation right here. Okay, awesome. So the last thing is, okay, well, if we want the projection of v onto u, right? Suppose that we want the vector projection. Okay, if we want the vector projection, which it will be, if you take an exam or something, right, they will tell you if they want the vector projection. But if you want the vector projection, then not only do I want the scalar value that comes out of this, I also want the direction of what I'm projecting it onto. So in this particular problem, okay, in this particular problem, I am interested in the projection of v onto u. So I'm going to say, well, if I'm looking at the projection of v onto u, I actually don't care about the magnitude of u, right? If I don't care about the magnitude of u, then I actually want the magnitude to be 1, because when I multiply them together, then I don't want this to be adjusting the length of my projection, right? So therefore, we use the exact same equation as before, right? Which is going to be v dotted with a unit vector of u, which will be u divided by the magnitude of u, right? This is going to be a scalar, okay? And then I only care about what? The direction of u, because this, at the end of the day, points in the same direction as u. Therefore, if I only care about the direction of u, I again use the unit vector times. So it does look a little bit funny, right? The equation looks a little bit funny, but that's what it turns out to be, okay? So this equation should be something that goes onto your formula sheet, all right? And that is this arrow right here. Excellent. All right, so moving on to page 3, we have an example. All right, so this example is asking us to find the projection of v onto the line AB if v is equal to 3 comma negative 4 and A is the point 1, 1 and B is the point 4 comma 5. Okay? So the first thing I need to do is say, okay, well, I know the points A and B. How do I find the vector AB, and more importantly, the unit vector of AB? Because recall, I actually don't care about the length of AB, right? Because I only care about the direction. So the first thing I need to do is figure out what the vector AB is. Okay, in order to do that, I'm going to subtract the x values from each other and then subtract the y values from each other in order to find the x and y components of my vector. So I like vectors that have positive components. In this case, okay, well, let's see. If it's asking me for the magnitude of the projection, it shouldn't really matter, right? Because the magnitude of the projection will just be a positive number, okay? But if it's asking for AB, then it's asking for the vector that goes from A to B, right? Like this. So therefore, I'm going to take the coordinates of B and then minus the coordinates of A from it, right? So it's going to be 4 minus 1, comma 5 minus 1, which will give us a unit vector, or a vector of 3, comma 4. Okay, great. And therefore, I'm able to plug it in to our previous equation, right? Of course, without first finding the unit vector. If you wanted to just take the equation on the previous page as it is, then the unit vector, we can just solve for the unit vector while you're doing it, but we'll take it step by step here. So the unit vector for AB is going to be the vector AB divided by its magnitude, right? Which will be 3, comma 4 divided by the magnitude. Recall using the Pythagorean theorem, which would be the square root of the x component squared plus the y component squared. So it will be 3 squared plus 4 squared, which will conveniently give us 5 in the bottom. So we have 3/5, comma 4/5. All right, great. Then we actually just follow the equation on the previous page, and we can say that the projection is then equal to 3, comma negative 4 dotted with 3/5, 4/5, and then all of that just being multiplied into or distributed into 3/5, comma 4/5. Okay, so we can work, let's separate this, right? So we can work this math out right here. We end up with, so this is, remember, this is going to be a scalar. If you don't get a scalar coming out of this, then you done messed up somewhere, okay? So you end up getting 9/5 minus 16/5, of course, doing 3 times 3/5, which is 9/5, and then negative 4 times positive 4/5, which is negative 16/5, okay? This, which gets multiplied by 3/5, comma 4/5, and then this turns out to be, what, negative 7/5 times 3/5, 4/5, okay? Which then, of course, you just distribute into here, and then you get negative 21/25, comma, negative 28/25. So this is the vector projection for, and this is the vector projection for V along the line AB, okay? So it's as simple as that. Every single time it asks you for a vector projection, you are going to follow the exact same steps that I just did above, okay? So they're relatively straightforward, okay? You're not gonna need to do anything fancy with them, okay? Sometimes they'll actually give you the vector AB to begin with, so you don't have to do this first step, but in general, just follow these steps, you'll be in good shape. Okay, great. So another type of projection I wanna talk about is the projection that you're most likely going to see in this class. It's a little bit simpler, okay? This is kind of just here to warm you up for what you're gonna use for the rest of the course. It turns out that the projections that we use in this course are not actually as complicated as what we just described here. This is more of a learning tool than anything else. Okay. Suppose I have a force that acts 40 degrees from the vertical. Okay, but a force that's acting 40 degrees from the vertical, the magnitude just happens to be 20 newtons. Fantastic. All right. Now, I can figure out the x and y components by using trig, as you would expect, right? Now, the x and y components are going to be very important to us in this class because in general, we think about things like left, right, up, down, okay? So if we look at this, it's a 40 degree angle. Okay, well, I don't really know how to quantify that when I'm doing calculations, right? If we split things up into their x components and y components, then we should be in good shape, okay? So it turns out that the x component is going to be this right here, and the y component is going to be this right here. So note their directions, okay? So the x component is going to be negative 20 times the sine of 40. And the y component is also going to be negative because it's pointing down, okay? Of course, according to these axes, of course, when we do three-dimensional stuff, the axes might be all turned around and stuff like that, but you just need to go according to your axes. This I drew pointing down, of course, in the negative y direction, so it will be negative 20 times cosine of 40. Now, we have to be very careful when we do this because the placement of the angle is going to determine, right, which one's sine and which one's cosine. Now, I usually in this class, the angle will be made with the horizontal. Okay, just like most of the time it will be made with the horizontal, in which case your x component will be cosine and your y component will be sine. But I threw you guys for a loop in this one just to keep you guys on your toes. All right. So we have this. In general, I like to keep these as they are. I don't plug it into the calculator if I can help it, okay? Because writing this helps you understand that this value came from here, okay? Because if I go ahead and write it in my calculator, it turns out to be, you know, some decimal, and then I'm looking through my work and all of a sudden I'm like, okay, well, where did this decimal come from, right? It's much harder to troubleshoot something that's a bunch of decimals than it is to troubleshoot something that is very specific. It says 20 cosine 40 because I know those values came from here, okay? All right, so it turns out that the x and y components here, if you use Pythagorean theorem, it will generate 20, which makes sense, right? The magnitude of f you would expect to be the square root of fx squared plus fy squared, right? And if you want, you can verify that by yourself. How does that work? Well, sine squared plus cosine squared equals 1. That's Pythagoras, right? My boy Pythagoras. Okay, so one of the things I wanted to talk about is an application to axes that are not parallel, okay? So suppose I have, such as drawn in the bottom of page 3 in the notes. Suppose that I have an A and B axes. That look like this and they're not parallel. Actually, I'm going to draw it even less parallel because how about like that? All right. So I have A and B axes, and there's some force P equals 10 newtons. Now, one note about using letters in this class. Of course, it makes sense to use capital F as force. You'll see me use a few different letters in there, but for whatever reason, capital P is also used as a force in this class. Why? I have no idea. But I will alternate between them to get you guys ready for the monkey wrenches that they're going to throw at you. So this is 25 degrees, and this is going to be 35 degrees. Okay, so if I use the classic approach that we've used in the previous problems, I can easily figure out that the projection of P onto A, the projection of P onto A is going to be 10 times the cosine of 25, and the projection of P along B is going to be 10 cosine of 35, right? Which makes sense because these, right, it would be this right here and this right here. Great. Now, if we try to use the Pythagorean theorem to find P from its projections, then we will run into a problem, and we'll see why. Right, so I'll put a question mark here. And so PA squared plus PB squared, and then is it going to work? I don't know. I'm going to run out of space, but okay. If you plug this into your calculator, you will find that it does not indeed work out to 10. So why is that the case? Okay, well, so why did it work for the previous problem where we had x and y components, and why did it not work for this problem here where we had a and b components? Well, the trick is a and b are not perpendicular. Okay, so a and b do not form a perpendicular set of axes. Of course, we can choose any set of axes that we want to work with, but you know, choosing axes that are perpendicular are going to help us a lot more. This is one of those cases where you care about an off axis. We may talk about that a little bit later on. Okay, so note that this is not true. Okay, this is not true. And we also have to know something else too, that the vector projections of PA and PB don't actually add up to P either. So if we try to do this, we find that it's not actually equal to the vector P, right? If we add these vectors up, what do we get? So like I said, you have one vector here, one vector here. If I add this head to tail, right? I just take this one, I copy it here, right? It turns out to be this. Well, the resultant is not this original vector, okay? So we have to ask ourselves, why is that the case? Right, and like I said, it just turns out that it's because A and B are not perpendicular. So now we need to say, is there a way to find quote unquote projections of P so that this is true and this does come out to be correct? Okay, so that will be called components. All right, so the two major topics that we're going to talk about with vectors are projections and components. Okay, so I consider projections to be the easier one. It turns out also that we use projections for the entire course. Like I mentioned, it's the topic in the notes that's right above this, just finding the x and y components, right? That's pretty much the extent of projections that we're going to use throughout the course. But now I want to talk about vector components. Okay, so vector components requires a little bit more geometry, but I think we'll be just fine here. All right, so moving on to page 4 in the notes. Okay, I'm going to draw the same diagram, but a little prettier. Okay, so components will let us do CA plus CB equals F. So like I said, we're going to draw the same exact diagram, which will be lower. This is going to be 25 degrees, this is going to be 35 degrees. Okay? All right. So, when it's asking you for the components, all right, now on an exam, it will ask you for projections and components, so you'll know for sure which one you have to use. You will not have to guess, okay? But I just want to make it clear that components will add up to the original value, and projections might not necessarily do that, okay? Projections only add up to the original value if the axes are perpendicular, okay? So the first thing we're gonna do, you might be wondering, Scott, why did you draw these lines so far out? And you'll see why in a second. But the first thing that we wanna do is draw a parallelogram, okay? This is what we call the parallelogram rule, right, for vectors. And all we're gonna do is look at the head of our vector, and then we're going to draw axes, two axes, that are parallel with our A and B existing axes, okay? So I'm gonna look at my A, and then I'm gonna just basically make a new line that's right here, which is going to be We can call it A prime, call it whatever you want, right? It's not perfectly parallel, but you guys get the point. All right, and then B prime, which is going to be this, okay? Now, we need to say, where is the parallelogram that we're interested in? Well, it is right here, okay? But it's interesting that this is called the parallelogram rule because it turns out that we don't actually need the entire parallelogram. We only need half of it, right? Either the top half or the bottom half, okay? So what I always like to do, and I always recommend this to everyone when they do a parallelogram rule problem, is that they take whichever piece they use, top or bottom, it does not matter, okay? They take the piece and they redraw it, okay? I always recommend it because doing all your calculations on this is very sloppy. If you redraw it, it becomes a lot simpler, all right? So I'm gonna redraw P. My marker's dying, of course, but I'm gonna redraw P, and then this is going to be our side B. This is going to be our side A, and notice that this side A is the same as this side A, this side B is the same as this side B, hence it's a parallelogram, right? So this will be our side A. Now, this is a 35-degree angle, and because of geometry, right, this will be a 25-degree angle, and this will be a 35-degree angle, right? So this will be our 25-degree angle. Of course, we could figure out what this top angle was because we know that all the angles inside a triangle add up to 180 degrees. All right, so if we do that, it turns out to be 120 degrees. Great. So we know what P is. I think I have it written here somewhere. Oh, we just used the same P from before, so we said P is equal to 10 newtons. We are interested in finding the components along the A axis and the components along the B axis, or rather component, right, single component. Now, inside, right, this triangle, we know all three angles and we know a single side, okay? So if we don't know two sides, okay, if we don't know two sides, then we will use the law of sines. And for those of you who are not familiar with law of sines, the law of sines looks something like this. And I'll actually just use this as an example, okay? So it's going to be, well, actually, which version? Okay, so I use F. Top, so P, which is 10, let's just drop 10. So 10, right, which is the value of P, divided by law of sines, right, so sine of the angle that's opposite of this. Okay, there's only one angle that's opposite of P, and it's 120 degrees. Okay? Equals the other one, which is A, right? The side A divided by the angle that's opposite of A, and there's only one angle opposite of A, it's 35, so sine of 35 degrees, and then of course you guessed it, it's B divided by sine of 25 degrees. Okay, so this is kind of like one of those weird equations where it's like the equals equals. All you gotta do is say, well, I know what this is, right, because I know everything here, so all I gotta do is just cover this, solve for A, right? It turns out that A, I don't know if I wrote the values here. Oh, you guys know how to solve for them, right? So cover this, A equals something something, and then after that, you cover this and say B is equal to something something, right? So you're able to solve for A and B independently. Of course, if you covered this, it really wouldn't make any sense because you have two unknowns and one equation. Okay, great. So we're able to solve for A and B, or in the notes I have written as the components of A and the components of B. Great. So now what? Okay, now what? So in this class, okay, I'm going to show you guys how to solve problems like this, and I'm also gonna try to help you guys view problems in a different way as well, okay? So, of course, you're not gonna get this exact problem on an exam. You might get a different variation of it, so I wanna help you guys understand and look at problems from different ways, okay? Great. So, suppose we only know the components of A, the component of B, and the angle between A and B, right? And we don't know the value in the middle, okay? So just a slightly different scenario here. Right, so I know, so this is A, this is B, right? I know CA, I know CB. I'm interested in and I know the entire angle between them is alpha, right? The entire angle, so not just the top or bottom, right? The total, okay? What is P, right? So P is equal to question mark. Now, how do I find that? Well, that is going to be law of cosines, right? So we figured law of sines, we already used that above. Now, if we're interested in finding a single value of length, right, a single length value, usually we're going to use law of cosines. If you're interested in finding two values of length, such as the components of A and the components of B, then most likely you'll be using law of sines. Okay? So in this case, right, the law of cosines is going to equal, so it's P squared equals CA squared plus CB squared plus 2CA times CB times cosine of alpha in between. Okay? So you may be wondering, like, hey, well, and also just complete the picture. This is CB, right? So you may be wondering, well, hey, there's a version of law of cosines that I've seen that has a negative here, right? Well, that scenario actually is this. Okay, which makes sense because this is the shorter side, right? That connects them. Of course, until the angle gets large and then cosine of alpha is negative and all this stuff. But in general, this is what we're looking for. Okay, awesome. So just a note before we move on to the last topic of this lecture. In general, okay, you need 3 pieces of information from a triangle in order to know the triangle, okay? So like I said earlier, we were kind of talking about these triangles here. You either need a side, and an angle, such as CA, CB, and then the angle alpha between them, just like this, okay? You either need a side, angle, which is what we had in the previous one where we had law of sines, right? We knew the 25-degree angle and the 35-degree angle, and then we knew the one side of P equals 10 newtons, right? And we were able to solve everything else. Or you need a side, and a side, okay? If you know the 3 sides of any triangle, you're able to figure out the angles inside of them. Now, what did I leave out? What if you know an angle, and an angle? Well, earlier we were able to solve the 3rd angle using the other 2, so therefore being given 3 angles is actually redundant, so we don't need it, okay? All right, cool. So the last topic of the day that I would like to talk about is Newton's laws, all right? And Newton's laws is of course used in this class, right? Because it is a physics-based class, but there will be some restrictions that we're going to use. Now this is sort of like a review. Deforms, I don't think it's wise to wait until deforms and dynamics to go over this, so that's why I'm going over it now here. Okay, so Newton's laws, of course, in general. The Newton's laws, of course, that are applicable to this course. So F equals ma, you guys are all familiar with that. Perhaps without the vector signs, but they end up being the same thing because you can break them down into their x, y, and z components. The units for our force is going to be newtons. The units for our right? Mass is in kilograms. Of course, our acceleration is going to be meters per second squared. Okay. Now, this class is called statics, right? We said everything in this class does not move. Therefore, everything is going to be equal to 0. More specifically, the acceleration is going to be equal to 0, right? And the net force is going to be equal to 0, okay? Couple notes about notation. So the first thing is when I write units in brackets like this, it just means that it is a unit, right? And then of course we can kind of do like unit, quote unquote, unit analysis here, right? So just to not confuse you guys. Secondly, when I write summations, they're gonna look ugly like this. So I try my best to write them nicely, but I will say summation when I write it. Okay, so because the class is called statics, right, the acceleration is equal to 0, therefore all of the scenarios of forces and moments in this class are going to be equal to 0. So the sum of the forces in the x direction equal to 0, sum of the forces in the y direction equal to 0, and then sum of forces in the z direction equal to 0. In addition, the sum of the moment is equal to 0 as well. So you might be wondering, what is the moment, right? I'll explain to you guys towards the bottom of this page and probably into the next lecture as well. But the moment is talking about rotation, okay? Rotation. All right. In general, our weight is equal to mg, right? That's pretty self-explanatory, right? The weight of something in newtons or pounds is equal to the mass of that object multiplied by the gravity. In this particular course, the Virginia Tech version at least, you have to use 9.81. If you guys are doing like the online homework and you use 9.8, it will not like your answer. So be sure to use 9.81. I've caught that L many times. Okay, so it's of course meters per second squared, or of course 32.2 feet per second squared if you're in freedom units. Okay, so there's that. Now, the mass is going to be in kilograms or slug. Okay, so now this comes to a very important topic or note, right? Of course, in kilograms, it's pretty natural to just write your mass as kilograms. If a problem gives you something in pounds, you have to divide it by 32.2 to get the mass, okay? So if it says, oh, you know, I weigh 165 pounds, right? In order for me to get the mass, right, the usable mass for the problem, I have to divide it by 32.2. Okay. So the last thing I want to talk about before wrapping it up is moment. Okay, and I will go into more detail with in the next lecture. But for now, I want to introduce the topic so you can brew some stuff in your head. Okay, so a moment is a twist or bend caused by applying a force at a perpendicular distance. Okay, so let me draw it out. Okay, so what the heck does that mean? This is my point of interest, okay? And suppose I have a lever here, right? So this circle right here, I have a lever. Now, if I want to rotate this, suppose it's like a screw or something like that, if I want to rotate it, does it make sense for me to apply a force in this direction, right? It'll push it in, right? Nothing's going to happen, okay? If I want to rotate this thing, I need to apply a force in the perpendicular direction, right? I need to apply a force in the perpendicular direction. Now, it turns out that we have a convention for, a sign convention for moments, just like we did in forces. Of course, we know that up is positive, down is negative, right is positive, left is negative. It just so happens to be whoever made physics up just determined those to be the units that we, or the directions that we used. It's sort of the same thing with statics, right? So whoever made statics up just said, hey, a clockwise rotation like this is going to be negative. I know, boo-hoo, right? and a counterclockwise rotation is going to be positive, right? So a little counterintuitive, but once you get the picture, you will be just fine. Now, I will go into more detail about this in the next lecture, but for now, I just wanted to introduce the idea to you. So, I'm going to actually grab something to use as an example. All right, so I've got one of these really neat foldable desk lamps, okay? So for simplicity, I'm gonna fold one of the things down. So I've got something that looks like this, okay? It can swivel like this, right? So if I wanted to actually move, here, I can just do this, right? Move this, okay? I need to apply a force that is not pointing into the point of rotation, right? So you guys would agree that this hinge, right, is where this whole unit rotates about, right? So if I were to push directly into this hinge, nothing would happen. I'm pushing on it, nothing happens, right? In order for me to rotate this thing, I need to apply a force that is perpendicular, or it could be off perpendicular too, but we'll talk about that in the next lecture, right? I can push something like this and be like, boom, right? And do something to it, okay? Yes, if it's not strictly perpendicular, I can just point down like this and get it done, right? But the second I point directly towards this base or point of rotation, nothing happens, right? I can do it all day and nothing will happen, all right? So that is the idea of the moment, right? We will expand upon that during the next lecture. But for now, let's do a recap of what we talked about this lecture. All right, so in this lecture, I gave you guys an introduction to statics. So it says, what is statics? Okay, recall the 4 steps to solving any problem, okay? And we said, okay, first, what is going on? We looked at the bicycle. Next, we said we need to find the external forces and then the internal forces. And then the third step is looking at which equations we need to use in order to solve the problem, which of course we'll do throughout this course. And the last one is asking yourself, does my answer make sense? And recall that we can ask ourselves 3 independent questions to make sure that our answer is what we expect it to be, okay? The next thing we did was talk about scalars and vectors, and then in the vector world, we talked about projections and components. All right, and the last thing we did was, of course, talk about Newton's laws. In the next lecture, I will be going over an introduction to force systems. So this will just be applied forces only. We will not be talking about reaction forces or anything like that. And of course, we'll be doing moments as well. Hopefully, we'll get through 2-dimensional forces and 3-dimensional force systems in the next lecture. So I'll see you guys then.